quadrature area of plane curve in Cartesian coordinates. Here, let us consider a reference system, x-axis, y-axis. We consider a curve of a continuous function. AB is a curve of a continuous function y equals to fx defined on the interval a to b. Let AB be a curve of a continuous function y equals to fx defined on interval AB. Let us take 2 points P and Q on the curve. Point P and its coordinates be xy, and point Q and its coordinates be x plus delta x and y plus delta y, so that P and Q are sufficiently near to each other. So let us take points P xy and Q x plus delta x, y plus delta y on the curve. From the in point A, let us drop perpendicular on the x-axis, and AC is the perpendicular on x-axis drawn from A. That is, AC is the ordinate of the function at the point A. Let us draw another perpendicular line from P on the x-axis, and let this be PM. Then in this setting, OC is equal to A, OM is equal to X, PM is equal to Y. Let us consider the region APMC and its area be AX. Here PM is a variable ordinate and APMC area is the variable area and AC is the fixed ordinate. So AX denotes the variable area APMC bounded by the curve, the x-axis, and the ordinates 1 fixed ordinate AC, the fixed ordinate AC where OC is equal to A, and the variable ordinate PM, and the variable ordinate PM where OM is equal to X. Since coordinate of the point P are xy, so OM is equal to X. Again, let us drop perpendicular from Q on the x-axis. Let QN be the perpendicular. Since the coordinates of the point Q are x plus delta x and y plus delta y, so ON is equal to x plus delta x and QN is equal to y plus delta y. We consider the area of the region AQNC, and this region, this area is denoted by AX plus delta x. So also AX plus delta x denotes the area of the region AQNC bounded by the curve, the x-axis, and the fixed ordinate AC, and the another ordinate QN, and the ordinate QN where ON is equal to x plus delta x. ON is equal to x plus delta x and QN is equal to y plus delta y. Now if we consider the area of the strip PQMN, then this area is the difference of the two area AQNC minus APMC, and the difference of the area AX plus delta X and AX can be denoted by delta AX. So delta AX is the area of the region PQNM. Now we can write the area of this strip is the difference of the two area. So now area of the strip PQNM, which is delta AX, is the difference of the area AQNC, which is AX plus delta X, and APMC, which is AX. So delta AX is equal to AX plus delta X minus AX, and it represents the area of the strip PQNM is the area of the strip PQNM bounded by the curve, the x-axis, and the ordinates at P and Q, and the ordinate PM and ordinate Qn. Clearly, we can see that the area PQMN, which is delta AX, is less than the area of the outer rectangle SQNM. This area is included in this external rectangle. So this area delta AX is less than the area of the rectangle SQNM, area of the rectangle SQNM, and this strip area, which is delta X, is greater than the inner rectangle PRNM. So this area delta AX is greater than the area of the rectangle PRNM. Area of the rectangle is given by length into breadth. Here for the inner rectangle PRMN, height is PM and breadth is MN, and MN is delta X. ON is X plus delta X, OM is X, so MN is delta X. Coordinates of P are X and Y, that means PM is equal to Y. So area of the rectangle PRMN is given by area of the rectangle PRNM is given by Y into delta X. Y is the height and delta X is the width. So Y into delta X is less than or equal to delta AX. Delta AX is actually the difference of these two area. One area is AQNM, which is AX plus delta X. Another area is APMC, which is AX. So AX plus delta X minus AX is A delta X is less than the area of the outer rectangle SQNM, and its breadth width is MN, which is delta X, and height is QN. Since the coordinates of the point Q are X plus delta X and Y plus delta Y, so QN is Y plus delta Y. So the area of the rectangle SQNM is height Y plus delta Y into width delta X. Since Y is equal to Fx, so we can replace Y by Fx. Fx into delta X is less than or equal to AX plus delta X minus AX is delta AX is less than or equal to, since Y is equal to Fx, so Y plus delta Y is Fx plus delta X. So Y plus delta Y can be replaced by Fx plus delta X into delta X as it is. Now let us divide each term on this inequality by delta x. Dividing left hand side by delta x, we can write fx is less than or equal to, dividing a delta x by delta x, we get a delta x by delta x less than or equal to, dividing right hand side by delta x, we get fx plus delta x. Now let us take the limit as delta x tends to 0. So taking limit as delta x tends to 0, limit of the left hand side, limit of fx as delta x tends to 0 is less than limit of the middle side, limit of a delta ax upon delta x as delta x tends to 0 is less than or equal to limit of the right hand side fx plus delta x. When delta x tends to 0, limit of fx is fx. Now limit delta ax upon delta x as delta x tends to 0 is derivative of a with respect to x. By the definition of derivative, this limit is the derivative of area with respect to x. Is less than or equal to, when delta x tends to 0, then right hand side reduces to fx. Here we can see that derivative of a is sandwiched between fx's, value of fx. So we can write derivative of ax is equal to fx. Since derivative is equal to fx, so by definition fx, antiderivative of fx is ax. So we can write ax is the antiderivative of fx. Indefinite integral of fx, that is antiderivative of fx plus c. Let integral of fx be capital Fx. Capital Fx is antiderivative of small fx. So ax is equal to capital Fx plus c. Let this be relation 1. In the figure, we have OM is equal to x, and when this x becomes equals to a, when x is equal to a, in this case the ordinate PM coincides with AC. Here at the point C, x is equal to a. So but OM is equal to x, and when x is equal to a, this ordinate coincides with AC. In this case, the area APMC reduces to 0. So when x equals to a, PM, the ordinate PM coincides with AC, and so AA, capital AA, that is the area of region APMC becomes 0 when PM coincides with AC. So we can write, that is, this gives AA, when x is equal to a, the left hand side becomes AA is equal to, right hand side becomes capital FA plus C, capital FA plus C. That is, simply replacing x by a, we get this relation. But AA is the area of the region APMC when PM coincides with AC. That means AA is equal to 0. So we can write 0 is equal to FA plus C. This gives C is equal to minus FA. On the other hand, OM is equal to x, and when x is equal to B, in this case PM, when x equals to B, then the ordinate PM coincides with the ordinate at B, that is, PM coincides with BT. So when x equals to B, we can say that the ordinate PM coincides with BT. So PM coincides with BT, and the area of the region ABTC is the required area under the curve. So when x equals to b, then AB becomes the required area A. So this gives, replacing x by b in equation in relation 1, we get A small b equals to F small b plus C. And AB is the required area A, which is equal to FB, and C is minus FA. So we get the required area of the region is equal to FB minus FA. Since capital Fx is the antiderivative of small fx, so we can replace FB and FA in terms of integral. So we can write A is equal to, now FB is the integral of Fx when x is equal to b. Similarly, FA is the integral of Fx minus as it is. FA is the integral of Fx when x equals to a. So A equals to FB minus FA is the difference of the two integrals when x is equal to b and when x equals to a. Now we can write this difference in a single integral as definite integral from a to b of fx. So the definite integral of the function fx from x equals to a to b gives the area of the region bounded by the curve y equals to fx, the x-axis, and the ordinate at x equals to a and ordinate at x equals to b.